All right. So again, thanks everybody for being here. Today, we're gonna discuss about oversmoothing, oversquashing, heterophily, long range, and friends and their interplay. We're gonna let Adrian and Federico present. So yeah, the stage is yours.
Thanks, Fabrizio. Can you hear me properly, right? I think.
Yes.
Okay, cool. So thanks, Fabrizio, and thanks all the Glow organizers for letting us present this work. We are pretty excited for presenting this work and have the feedback from the community, because it's actually the goal of this work to foster the critical thinking about the community in this topic. So yeah, we are very pleased, both of us, to present. So yes, we are presenting today the paper that we call Oversmoothing, Oversquashing, Heterophily, Long Range, Demystifying the common beliefs in graph machine learning. Here at Glow, and was some of you already know, was desk rejected of NeurIPS, the position paper track for ambiguity. So yeah, let's see. Also, we would like to hear your opinion about if the paper is ambiguous. So yes, another just disclaimer, we will present also this work in a couple of weeks in Porto in the MLG workshop. We are also pretty excited, and also you're invited. If you're around, just feel free to reach us and go there to see all the workshop and the presentations. So the outline that we are gonna follow today, first, it's a little motivation of why are we doing this paper and what idea we wanted to convey in this paper. And then we will go through every problem separately. First, is oversmoothing really a problem? Then we will have a discussion about the concept of oversquashing. And finally, we will have another brief discussion about the homophily, heterophily dilemma. With the idea that the long-range tasks actually are not always, or could not be always defined just as an homophily, heterophily thing, or just as a bottleneck. We will briefly start before going into that specific problems with the motivation. So basically, and this type of project was originated as a position paper. So it was originated after some time working in these topics, both Federico and I, and realizing that we had not cleared some of the main definitions of the topics. It's not also only our thoughts, but we had many conversations with people in the field, in the community, in different conferences, in different venues. We collected all this feedback, and let's say it was a common voice in the community that some of the implicit assumptions or the formalization of these problems were not clear and caused confusion. We do not say that we don't understand the intuition of the problems at the first glance, but once you deepen in the assumptions and the formalization of the problem, many issues arise in the understanding on the topic. So yeah, we will see this in detail on each of the topics. And the goal of this paper is just to foster like a critical thinking about these topics, and most likely and hopefully promote new questions in the field in these problems as well, that we think that they are still very relevant. For that, we have read many papers, and we have tried to identify what are the beliefs and the assumptions and the statements that people, including us, we do in the previous papers that we do. So we have identified nine common beliefs grouped in three blocks. One is beliefs about oversmoothing, then beliefs about homophily, and finally beliefs about oversquashing. These are the 9 beliefs that we have identified. And we also have identified some of these broad assumptions or implications in a broad list of papers that we have also grouped there as a disclaimer. And I think this is very important. The goal is not at all to criticize the previous work. On the other hand, the previous work actually really led us to understand all these problems, build the foundations of all these problems. And after understanding all the previous work, we can actually identify these 9 common beliefs that even ourselves we made in some of the previous works. Yes. So as we will move forward in this presentation, we will just go through these 3 blocks, and we won't go in very detail on each of the definitions and blocks because we want to prioritize the discussion. So we will just define the common belief and show maybe just a couple of simple examples of what we mean. And after that, we will prioritize the discussion. Of course, for more references and more examples, you can check the paper. So I will start with the first set of beliefs about oversmoothing. So the idea is oversmoothing really a problem? And for that, we have to understand what is oversmoothing. Intuitively, we can understand it as the collapse of the embeddings to a non-meaningful subspace or constant as we increase the number of layers in our message passing neural networks. Basically, I think I have the cursor here. Yeah. Informally, we can define it this way, which in the limit in the number of layers, when the number of layers tend to infinite, some similarity metric over the embeddings, it leads to a constant. That's the intuition of oversmoothing, just to be everyone on the same page. I think originally they will count that from making diffusions with the random walk matrix or the hit kernel, that no matter the input distribution that is over your nodes, you will reach to some constant, no matter if it's this diffusion or this, you will reach to some constant, either the degree distribution or some constant, which is the average. On the oversmoothing literature, many works has analyzed the impact of the different parts of the DGNs, so like the activation functions, different architectures, feature normalization. But overall, with all of them make the same claims, especially when they are trying to intuitively explain the problem. So we have more examples in one tutorial that I made with Amelia Bellinger in ICML, and also preparing those slides were one motivation because I had to define these problems and also oversmoothing, and it was not so easy for us. So basically this, I won't go into the detail of the metrics, but this similarity metrics, one of the first problems is that we have many ways to measure it. Here I just have listed some, in the paper there are more, and also in the surveys, existing surveys there are more, but some of the most popular are the Dirichlet energy or their normalized version, which is the Rayleigh quotient, but there are many more. Just to keep in mind that there are many metrics, so in the discussion we also can discuss about it. So let's go with the first belief, which is that oversmoothing always happens. Usually, we have find it in the literature as oversmoothing happen regardless of the architecture, regardless of the activation function, etc. One simple counterexample, which is an example that we adapted from Roth and Liebig, basically is to multiply by 2 the feature norm. So for instance, we measure the Dirichlet energy over the layers, and first of all, for some of the architectures, Dirichlet energy does not collapse. So just a change in the architecture, it's a counterexample that if we define oversmoothing with Dirichlet energy, that does not happen. And then just if we multiply the feature transformation matrix by 2, then the behavior changes. So it might be a counterexample of that oversmoothing does not happen. Also, some of the works that we point in the paper, they look also in this direction and has also some critiques to oversmoothing, such as the effect of feature normalization, criticisms in terms that some of the works we use frozen weight networks. This point that oversmoothing does not always happen was also studied by Di Giovanni, where the Rayleigh coefficient, depending on the architecture, can converge to either 0, which would be oversmoothing, or to lambda n, which would be the maximum frequency on the graph. And there are way more works that point into this direction. If you are still not convinced, just one toy example is if you change just the aggregation function in a graph convolutional network from a mean aggregation to a sum aggregation, rather than converging the Dirichlet energy per epoch and layer, the vertical axis are the training epoch, and the horizontal axis are the layer, it explodes. So basically, that's another example of this belief. Of course, as I said before, if you use another metric, which is the Rayleigh quotient rather than the Dirichlet energy, the insights changes. The results of the analysis changes. For those that, for some of the architectures that previously were smooth, now they do not oversmooth. So depending on the metric, we will have different conclusions. So it's also a critique or a thing that we have to think about in the field. The second belief about oversmoothing is that it always degrades performance. And we claim that oversmoothing does not always correlate with performance, but performance is not always explained by the embedding collapse. There is some examples. Here we have the depth. In the vertical axis, we have the Dirichlet energy, and the accuracy is the color. So in this first example, like a convolutional network with a mean aggregation, it correlates with performance. So basically the red points are all here, but as we change by a sum aggregation, then the Dirichlet energy explodes, obviously, but the accuracy is very low. So here, actually, if we consider oversmoothing as Dirichlet energy going to zero, it does not correlate. Also, a figure from Rush et al. They show how some of the architectures, they do not show a collapse in Dirichlet energy, and they still show a bad accuracy. But also happens the other way around, that oversmoothing, this collapse does not always lead to bad performance, and that's something that we have called in the paper beneficial oversmoothing. And there are some works that already point that some oversmoothing might be good depending on the distribution of the features in the graph. First, you will have a phase where there is, let's say, oversmoothing between the communities, and it might be helpful, and later it will be full oversmoothing that might be harmful. On top of that, some of these works already point to the class separability, rather just the feature distribution and the class separability, rather than just the collapse. They also, some of these works, they say that despite the global collapse, with some distributions, the class separability is better. So these are generally the beliefs of oversmoothing that we've identified in the literature. Our takeaway here, our advice or suggestion would be to analyze the separability of the node embeddings of different classes as a better research topic, where we could analyze also the interplay with the labels and the performances. Just before finishing this part and starting the discussion about these beliefs of oversmoothing, one note, also many works, oversmoothing happen when you increase the number of layers of the message passing layers, but when you increase also the message passing layers, there's another phenomenon interplaying, such as vanishing gradients, overfitting, or feature over correlation that might interplay with also these problems. So it make even more difficult to isolate. There's some works there and also in the paper. So this is just one example of one paper that also was in this direction. It came out right after also we released the position paper. So we are happy to start the discussion about these topics. We would like to hear your thoughts about what you think about this topic.
Thanks, Adrian.
Thank you.
Thank you.
The screen, Federico?
Yes, Adrian, please. And of course, for those who ask questions in the chat, just drop us an email if we don't make it in time today.
Sure.
We're more than happy to answer. And I also want to, since I joined abruptly, I want to thank all the organizers for inviting us. So it's a real pleasure to talk to you and have this chat all together.
Of course.
So let me try to share. Maybe first I should go in presenter mode. I'm not sure if you see the screen.
Yes.
No.
You do, right? Okay. Let me move Windows. Okay. So yeah, the next part will be about oversquashing. We leave the homophily, heterophily dilemma to the end because it's a bit shorter. So when Adrian and I started to chat about all these issues, one of the things we couldn't agree with is what is oversquashing. So do we have a definition of it? Or not. And I mean, he started the section on oversmoothing by clearly defining it, at least in one way, right? But truth is, we don't know how to define oversquashing exactly. And if we can trace the the origin of the term back to 2021, I would say Uri Alon and Eran Yahav defined oversquashing as the exponential squashing of information that happens when you go through one of these bottlenecks on the left. So this kind of bottleneck. I don't know who of you have read this paper, but what let's say I think the oversquashing term originated from there. And then we had the paper from Topping et al., Understanding Oversquashing and Bottlenecks on Graphs via Curvature, where they defined this curvature metric based on the structure of the graph. So the first thing that Adrian and I started to discuss is that these are actually two different cases of bottlenecks. One is a computational bottleneck on the left because it acts on the tree induced by message passing when you compute a node embedding. So all this information you see is flowing through multiple copies of nodes that corresponds to the flow of messages to one specific node. And it might happen that you have a bottleneck. On the right, the curvature was defined based on graph theoretical measures. So once we started to, try to distinguish between these two cases, we could speak the same language again. And that was quite enlightening, at least to me, but for sure also to Adrian, because then we realized that there were some papers talking about oversquashing in terms of computational bottleneck and others in terms of topological bottlenecks. Others were confusing the two notions. So let's say probably this is just a matter of semantics, a problem of semantics, and there won't be, you won't see some big news in the next few slides. What I want to say is, for the sake of the presentation, that the topological bottleneck was typically measured using sensitivity. So the sensitivity is what you see here below, and you compute the norm of the Jacobian between a representation of node U after K message passing layers with respect to changes to the embedding of node V at layer 0 or, right in the middle of the message passing architecture. It depends on what you want to measure. What we defined as a computational bottleneck in the paper is the size of the computational graph that you are building for a specific node. So in this graph, we want to focus on the star graph and, sorry, on the node with a star in it. And then we apply 3 message passing layers. You see that in the flow of messages, there are multiple copies of the same nodes. If you consider, for instance, the star graph, it appears at layer 1, or at layer 2, 3 times. So it's the same representation multiplied 3 times. And so the more information you have, the larger your bottleneck, your computational bottleneck is. So the first belief, one of the beliefs about oversquashing is that it's related. It's essentially the same as topological bottlenecks, and these are measured as the sensitivity with the sensitivity metric. So we thought about a couple of simple examples to show that maybe sensitivity is not a great metric to measure the topological bottleneck. We have a simple graph with two communities, very small communities connected by, a shared node, let's say, and then we have the grid graph. If you look at the first one on the left, you see that there seems to be a topological bottleneck, right? There is this link connecting the two communities. But the computational bottleneck is mild in the sense that if you apply message passing repeatedly, and you focus on a specific node, you don't get an explosion of messages, especially because in this particular example, the number of nodes is small and you don't need many message passing layers to cover the entire graph. But if you look at the grid graph, then the computational bottleneck is much worse, and you don't have an evident topological bottleneck here. You can reach every node from any other node. The interesting part is that if you compute the sensitivity metric for both graphs, in both cases, it decreases with the number of layers. So even when you don't have a topological bottleneck, you can have low sensitivity. So this is just an example to warn you against maybe assuming that low sensitivity implies the presence of a topological bottleneck. The second belief is about oversquashing being the computational bottleneck, and here's where here's what I was thinking in the past. So oversquashing means over squashing. So just from the perspective of a computational bottleneck. Also in this case, what you could do to mitigate the computational bottleneck is to prune messages. So you focus on the computational graph or the computational tree induced by message passing on a specific node, like here, and you learn to prune some of these paths. And that should reduce the amount of information that needs to be stored in the root embedding of node 3. Now, this is kind of good, in my opinion, to mitigate a computational bottleneck, for instance, in the grid graph. However, it could be that by pruning some of these paths, you are actually you're actually virtually separating communities. Because if you cut let's say this link between the two communities from the perspective of the computational bottleneck, you cannot propagate messages long range, right? So this with this, what I want to actually say is that computational bottleneck and topological bottlenecks are for sure related problems, but they can be treated independently. And let's say, as independent problems. And one other example of this is if we think about rewiring approaches. So the rewiring approach can improve the topological bottleneck, right? Because you can reach maybe nodes that are far apart with just a couple of steps after additive rewiring at least. But if you consider additive rewiring from the perspective of a computational bottleneck, adding an edge can only worsen the number of messages that get propagated to nodes. So in our opinion, this is kind of a nice example to say they are for sure related. Message passing is the common link between the two, but you should treat them as separate, and we should speak about them separately and clearly distinguish between, whether we are working on one or the other bottleneck, type of bottleneck. Then there is the relationship between oversquashing and long range. This is yet another let's say, connection that is often made in the sense that oversquashing is considered to be problematic for long-range tasks. There are lots of statements saying, yeah, oversquashing is a problem in long-range tasks. I think this is a valid way of thinking because when you have a long-range problem, you typically need many message passing layers because you assume that every node needs to capture information that is far away. And clearly using many message passing layers induce computational bottlenecks because you have, an exponential, let's say, maybe it's not exponential, but a big growth of information, of the amount of information you then need to squash into a single node embedding. But then, now that we have the notion of computational bottleneck, let's just think about, a hub. So this node may have thousands of neighbors. And if you think about just applying one message passing step to this node, then you will for sure, unless you use, a huge embedding dimension, you for sure will have some lossy compression of the information around this hub. So oversquashing in terms of, not oversquashing, let's say the computational bottleneck happens even in short range tasks. So saying that oversquashing is problematic just for long range tasks may not be correct, maybe. But it's just because the oversquashing term is not clear. So if you think about this in terms of computational bottleneck, I think we can all agree that this is a problem both in long and short range tasks. But if you mention oversquashing, it's too ambiguous, let's say. And the other belief associated with long-range tasks is that topological bottlenecks are associated, are important in long-range tasks. And this is a bit tricky. We don't have a clear statement, let's say, but we have, we have an opinion about this. So the topological bottleneck may not be involved in the computation of the function that predicts the true label. So maybe even if you have a topological bottleneck, it's not important for the long-range task. There might be other paths that you can take to reach long-range information, and it's not just about getting that information, but it's about walking a specific path to solve the task, which might mean that, for instance, rewiring by adding an edge may be detrimental to performance because you first have to see a number of neighbors or, nodes along a path before you compute the actual solution. And as Adrian said, long range, the application of many message passing layers that can lead to oversmoothing, right? There are other issues there, like the vanishing gradient problem. In general, the attenuation of information because of the computational bottleneck. When you have a lot of messages to be compressed, then it might be that you lose some important information along the way. And the topological bottleneck can induce another bottleneck in the computational bottleneck. So it can make the computational bottleneck worse because there is another bottleneck inside the computational bottleneck of a given node. So there is interplay between the two bottlenecks. But again, in this specific, in the case of topological bottlenecks, maybe, assuming that it's related or associated with long-range tasks is not correct unless you make some assumptions explicit, which is also what I mentioned before. And yeah, that's the end of this part. So I don't know if somebody has questions.
Thank you. Thank you, Federico.
Okay. So essentially, we go to the last set of beliefs about homophily and heterophily. And I would like to start by discussing the belief that homophily is good and heterophily is bad. So GNNs are made for homophilic graphs. I assume that most of you or all of you know what homophily is, but in general, it can be defined on both the features, either on the features or on the labels. So nodes that are similar in one of these two, with respect to one of these two, tend to be connected in the graph. That's a homophilic graph. If this doesn't happen, then it's a heterophilic graph. what we want to say about it is that this is very common to read in papers about homophily and heterophily, at least in the introductions, right? Which is what sometimes causes confusion when you then, try to form are trying to form your own opinion about the state of the literature. But this is not always a valid line of thought, because in homophilic graphs, you you look at nodes similar to you, right? I mean, you think you need to look at nodes similar to you to solve the task. And this is an assumption that I'm discussing next. And since message passing looks at nodes that are close to you by default, right? At least that's how the most message passing layers work. Message passing is a good inductive bias for your problem. Now consider a couple of examples. On top, you see a fully heterophilic graph where you can achieve perfect accuracy by using just one message passing layer. So all node features are set to the constant value of 1. You perform some aggregation and you have solved the task. You can solve the task perfectly. So there exists at least one case of a fully heterophilic graph where message passing is the perfect architecture actually for solving it. If you apply an MLP to the individual nodes, you do random chance, or yeah, depending on the probability on the fraction of nodes of in each class. Whereas message passing, yeah, it's just the model you would like to use. And in the second example, we have at the bottom we have a fully homophilic graph, which is long range. So you don't need to look at your neighbors to solve the task, even if the graph is homophilic. So in this particular case, a node is in class green if it's a distance greater than 5 from a given source node, right? We just defined arbitrarily this task. And I mean, these two alone are sufficient, in my opinion, to convince you to some extent that the belief is not always valid. And the second belief that we try to challenge is that we should evaluate long range, the ability of message passing to capture long range, let's say, interactions on heterophilic graphs. I know that there are a lot of benchmarks on heterophilic graphs like Squirrel, Texas, where it seems to be that message passing doesn't perform as well as an MLP, right? As a structure agnostic baseline. But you can see here that there is an example where this is not actually valid. So you can have a fully homophilic graph or almost fully homophilic graph that is still long range. You can have a fully heterophilic graph where you just need one message passing layer to solve your task. And so perhaps I anticipate a bit the conclusion of next slide, but perhaps we should remind ourselves that it is the task that induces homophily or heterophily on the graph. It's not like homophily it's not the converse. So it's not that homophily defines the graph. So if the graph is defined in particular ways, then what we often believe doesn't hold any longer. This brings me to the next belief, let's say, which is a bit more subtle, but often used to justify the previous beliefs. And the belief is that different classes, I mean, nodes that belong to different classes tend to have different features. And these features could be separable to some extent, because you assume that two communities share different properties. If you make this assumption, then the previous line of thought that I told you, that I described you, is correct. At the same time, why would you need, in general, message passing if if nodes of different classes already have different features? So why don't we just apply an MLP? Because the features are already separable to some extent. And this goes also a bit back to the discussion on oversmoothing, where we claim that what matters actually is improving the separability of embeddings. What you really want to have is that message passing helps you to better separate classes. But yeah, this is a pretty strong assumption that is often made in papers implicitly. And so if you read and you don't pay attention to it, you might fall into the traps of previous beliefs about homophilic and heterophilic graphs. And so for all of them, as I said, it's the task that induces either homophily or heterophily. And what you really need to study is the interplay. So how the task, the structure, and the features on the node, are related to each other, which is not simple. We don't know, I think, how to do it yet. We probably need to make big assumptions, very strong assumptions, and start thinking about how message passing works in those very naive and very toy settings. Then we can maybe move on to better understanding how message passing should even be done. If message passing is actually good for many classes of graphs, or if it's just good for a restricted set of problems. And that would allow us probably to move beyond and to make real progress in this sense. I have a last slide, which is about summarizing all that we said. I'm not sure if I should go through all the points. Perhaps in the interest of time, I will just, say the most important take-home message that we would like to leave you with, which is let's embrace critical thinking. So let's have a look again at the papers and let's try to understand that we already read. Let's try to understand what assumptions were made in these papers and if we really understood these papers. Because it happened to me that I reread a paper after doing this work and I came to different conclusions. So, and at the same time, let's try to focus on as I said, on the interplay between the task and the information on the graph. And that's all from us. Thank you.